So my dear students, in this lecture we are going to look at design of synchronous counters. We will be looking at mod n counter. How exactly we can design mod n counter, we will be looking at it. Mod n counter. This n can be any value, of course. If n is 5, I say mod 5 counter. If n is 4, mod 4 counter. Okay. So let us look at how many number of flip-flops required and how to proceed with the design. Let's say if I have a 3 flip-flops. With the 3 flip-flops, how many states is possible? Is 2 power 3. How many? What is 2 power 3? 8 states. What are they? They are from 0, 0, 0 to 1, 1, 1. Okay. So if you want in general some n, okay. So what we need to do is, for example, if instead of 3, if I say n, how many states I will get? 2 power n states I will get. But what I am looking for, in general, I want n states. So your 2 power n should be greater than or equal to capital N. Let's say n is equals to 5. Let n is equals to 5. So 2 power n should be greater than or equal to 5. For what value of n? For example, if I take n is equals to 1, 2 power 1 greater than or equal to 5? No, wrong. 2 power 2 greater than or equal to 5? Wrong. 2 power 3 greater than or equal to 5? Yes, correct. So here small n is equals to 3. That means to design mod 5 counter, I need 3 flip-flops. This is how one has to find the number of flip-flops required. Let's say n is equal to 6. Same thing. What is that? 2 power n should be greater than or equal to 6. For n is equals to 3, very first time it will get satisfied. 2 power 3 should be greater than or equal to 6. Okay. So this is what exactly the minimum value of 2 power n we need to take. Don't say that 2 power 10 greater than 10 power 6. 2 power 10 is 1024. 1024 is greater than, okay. So we have to seek the minimum possible value which is going to satisfy this condition. So this value should be greater than or equal to n. What does that mean? 2 power n should be greater than or equal to capital N. Okay. This is what exactly we need to do it. Upon doing this, what we come to know is, now we require 3 flip-flops. Okay. Now in the problem, generally nothing is mentioned. If nothing is mentioned, you can go for any flip-flop. If something is mentioned, you can go for that particular flip-flop. So now let us take mod synchronous. Let us take the problem. Let us design mod 5 counter. Mod 5 counter using JK flip-flops. Okay. So I need 3 flip-flops, obviously. So what I try to do is, I try to take up the present state, next state, and what exactly the excitation required. What is meant by mod 5 counter? We need to understand. Initially the value of the counter is 0, then it will become 1, then it will become 2, then it will become 3, then it will become 4. After reaching 4, what exactly happens is, it is going to 0. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 0. In mod 5 counter, you never come across 5. It will be 0 to 4. 0 to 4 will be 5. Is that okay? Now this is called state transition diagram. How exactly it is moved from one state to other state. If present state is 0, next state is 1. If present state is 1, next state is 2. If present state is 2, next state is 3. If present state is 3, next state is 4. This is what exactly the meaning of counter counting from 0 to 4, which is modify counter, right? So this is transition diagram. This is the basis for, okay, this is the basis for writing the present state, next state and flip-flop inputs. Now what is the meaning of this is we will look into it. Okay, so let's say there are three flip-flops QA, QB, QC. Okay, then what exactly we have? QA plus 1, QB plus 1, QC plus 1. Next states. So what is the meaning of this state table is I am trying to explain first, then we will look into it. Let's say 0 0 0. What is the value 0 going to next state as 1 0 0 1. If present state is 0 0 1, where it will go to? It will go to 0 1 0. If it is present state is 2 0 1 0, it will go to 0 1 1. If present state is 0 1 1, it will go to next state as 3. 3 is next state is 4. So 1 0 0. If present state is 1 0 0 4, next state is 0 0 0. What is the next state for the rest of the cases? Say for example the next present state is say 1 0 1. What is the next state? There is no next state. Similarly for the rest of the cases, what are the rest of the cases? Like 1 1 0, for 1 1 1, your next states are doesn't matter. Okay, this is exactly converting your transition table into transition state transition into a table saying how exactly your flip-flop has to move. We have three flip-flops. If they contain first 0, upon application of the clock it should become 1. Then upon application of the clock 1 becomes 2. Upon application of the clock 2 become 3. Upon application of the clock 3 become 4. Upon application of the clock 4 become 0. Upon application of the clock it has to repeat. Once it reaches 0, it is going to repeat the same cycle. And if there is any input which is greater than 4, for that output is doesn't matter for us, or we can also take it this as 0 0 0. By mistake this circuit enters into a state unknown state. This is unknown state, this is unknown state, this is unknown state. Okay, we may take it as don't care, in which case what is the value that you are getting next in the next state is doesn't matter if I say don't care. Or if I say instead of that, if I say 0 0 0, that means if any unknown state is entered into the flip-flops, then it will come to a known state 0. From there it is going to start from the very first state. If I take 0 0 0 0 0 0, by mistake some other state enters into the counter, by default it will reach to the initial state 0 0 0. Upon application of the clock pulses, it will be counting from once again from 0 to 4, then 0 to 4, so on and so forth, as long as clock pulses are there. Okay. Now what we have found so far is we have know that what exactly the present state. Okay, present state. What exactly the next state? So we got present state and next state. Once you know the present state and next state, From present states and next state information, what I can get is, I can get what exactly the flip-flop inputs such that this present state to that particular next state is possible. So we need a particular flip-flop excitations so that whatever I am expecting from the circuit, I can get it. That means if you know that QA is going from 0 to 0, what should be the inputs for QA? Let's say this flip-flop is JK. For JA, KA, what inputs I am supposed to apply? Such that I will get 0 to 0 transition, 0 to 0 transition, whereas this is 0 to 1 transition. Whereas here 0 to 0 transition, 0 to 1 transition, 1 to 0 transition. For each and every flip-flop, we have to write what exactly the flip-flop excitations are, flip-flop inputs that we need to write. Okay. So once you write that, you'll get the complete table, and from that table what I can do is I can complete the design. Let us write the state table. What we are writing so far is called state table. This state table consists of present state, next state. Okay. Then what exactly? Flip-flop inputs. What is the present state with respect to, let's say, QA, QB, QC. Next, QA plus 1, QB plus 1, QC plus 1. These are the flip-flops. Now for the flip-flop inputs, for every flip-flop there will be two inputs, JC, KC, JB, KB, JA, KA. Okay. Now let us complete the table first. Then you will have a excitation table for your reference, as we have seen in the last lecture. Excitation table for JK. What is JK? Q of t, Q of t plus 1, J and K. 0, 0, 0, 1, 1, 0, 1, 1. For 0, 0, 0 don't care. For 0, 1, 1 don't care. For 1, 0 don't care 1. Okay. Then 1, 1 don't care 0. This is excitation table. So we use this excitation table to get these JC, KC, JB, KB from JA, because for these flip-flops I know present state and next state from its functionality. What is its functionality? Is a counter. What it will do? It will go on counting. It is moving from one state to other state. So what is that? Is if it is at present state of 0, it will go to the next state as 1. If it is at present state of 1, it will go to the next state of 2. If it is at the present state of 2, it will go to the next state as 3. Okay, 0, 1, 1. If the present state is 0, 1, 1, it will go to the next state as 4. If the present state is 4, it will go to the next state as, what is the next state to the 4? Is 0, 0, 0. What is the, if the present state is 5, now we take it as don't care. Next state 1, 1, 0, also don't care. Then next state 1, 1, 1, 1, 1, 1, also don't care, don't care, don't care. Okay. So once we do this, I need to compare QC, exactly QC, with QC plus 1. Okay. Then I need to get JC, KC, JB, KB, JA, KA. Similarly, now let us do the JC part. QC, QC plus 1, 0, 0. For 0, 0, 0 don't care. So it is 0, don't care. Next, for 0, 0, 0 don't care. Once again. For 0, 1, For 0 0, once again 0 0. Compare this 0 with this 0, this 0 with this 0, this 0 with this 0. So 3 times 0 dot case. Fourth time, this is 0, this is 1. For 0 1, what is the input required? 1 don't care. So write 1 don't care. Right? Similarly, we need to proceed with rest of the cases. So what exactly that is going to happen is, for the next case 1 0, for 1 0, for 1 0, don't care 1. So it is don't care 1. When we are having next stage as don't care and present state is something, so obviously doesn't matter, doesn't matter, doesn't matter. Okay. Is there entry called one don't care? One don't care for here? No. Okay. So only for 0 0 0 1 1 0 1 1 we have. So for one don't care, one don't care, and one don't care. So when your next state is don't care, so your input is also don't care. Means to what state it is going, if you are not bothered, you are also not bothered about the inputs. Similarly, what we need to do is we need to compare this with this, then this with this. 0 0, what exactly 0 0? 0 don't care. Next 0 don't care. Next 1, see here it is 0 0, but it is 0 1. So it is not 0 don't care, instead it is 1 don't care. So this should be removed, it should be 1 don't care. So let us take the pen. 1 don't care. So this is 1 don't care, right? Similarly, I need to proceed further. 1 and 1. What is 1 1? 1 1 is don't care 0. So write don't care 0. Next, this one should be compared with this 0. 1 0. 1 0 is don't care 1. 1 0 is don't care 1. Next, so for how many written? 4 cases we have written. Next, fifth case. What is the fifth case? Fifth case, this is 0 and this is also 0. 0 0 is what exactly? 0 don't care. Okay, right? So rest 3 are don't care, don't care, don't care, don't care, don't care. Similarly here for J A K also don't care, don't care, don't care, don't care. Right? So what do I need to do? What I need to do is I need to write J A K. So compare Q A plus 1, 0 1. For 0 1, 1 don't care. Next, what is this is 1. What about this 0? 1 0. For 1 0, don't care 1. Okay. Next, what exactly that I need to do? Further you compare, how many we did? 2. Third one, third 0. What about QA plus 1? 1. So 0 1. 0 1 is 1 don't care. Next, what exactly? 1 0. For 1 0, don't care 1. Right? Fifth case. What is the fifth case for QA? It is 0, whereas this is also 0. It was 1 0 0 0. So 0 0, for 0 0, it is 0 don't care. Right? So this is how exactly we have obtained a state table. Present state, next state, flip-flop inputs. Okay. Now this flip-flop inputs, from where we are obtaining? From the present state we are applying. Okay. So flip-flop inputs are the outputs, or I can say flip-flop inputs are function of present state. From the present state information, we need to obtain flip-flop inputs. So these flip-flop inputs, we say these are inputs, but these are the outputs from present state being processed. So what I try to do is, I have a couple of flip-flops. From these flip-flops, what I do is I will take the present values of these flip-flops, I will give it to some circuit, and from there I will get some values. Those I will give it as inputs to the flip flops. Are you getting? So present state is input, and output after processing the present states is input to the flip flops, right? So what we have to get as a flip flop inputs is nothing but outcome of these states being processed. That means these are the inputs, these are the outputs. Or I can say in simple words, flip flop inputs are function of, okay, present state. So from this, what exactly is, I need to find the flip flop inputs. So these are nothing but how many? JA, KA, JB, KB, JC, KC. Totally 6 inputs I need to derive from the present state. So I need 6 K maps to get expression for JA, KA, JB, KB, JC and KC. Okay. So JA is function of QC, QB, QA. Similarly, all are function of present states. So how many variable K map required? 3 variable K map is required. So you take 3 variable K map, then what you do is you enter these values. What are the exact values you have to enter? I need to write a K map for Q. Okay, input variables are QA, QB, QC. Output I am getting is flip flop inputs. So you enter the values of JC, simplify it, I will get expression for JC in terms of QA, QB, QC. Okay. Similarly, KC. Similarly, JB, KB, JA and KA. That we need to do it. Let's do it. Okay. So further we need to simplify it. So what I will do is I will show you one sample K map here, so that remaining all you need to do it, okay, in a similar way, so that you will get an expression. Say for example I have like this. So how many inputs? 3 inputs. So 3 input K map I need to draw. That's fine. So what is exactly I have? What exactly I have is, let's say if I enter the values for JC, okay. So QA, QB, QC. So what is MSB? QA is MSB. Okay. QA is LSB, QC is MSB. So what we try to do is we will write okay, QB, QA, QC. When QC is 0, QC is 1. When QC is 0, what exactly? Lower values. When QC is 1, higher values. AB changing. So 0, 0, 0, 1, 1, 1, 1, 0. What is going to happen? 0, 1, 3. What about this 4, 5, 7, 6? Is it okay? 1, 0, 1, 1, 1, 1, 7. Okay. Now I have to enter these values. What are the values? JC values I need to enter. Right. If I enter here, what is value? 0 is 0. So it is 1 for 3. So 3 is 1. What is exactly? Don't guess. 4, 5, 6, 7 are don't guess. 4, 5, 6, 7. 4, 5, 6, 7 are don't guess. Okay. Is there any possibility for 8 ones? No. So what I can do is I can only combine this two. What is the expression for JC? JC is nothing but, what is exactly that I am getting is, this is 1 1. So it is QA QB. QA QB. Similarly, what I need to do? I need to do for KC. Take the table, enter the values of KC in the K map, simplify it, get the expression. Similarly, JB. Similarly, KB. Similarly, JA. Similarly, KA. Once you do that, then what is going to happen? You are going to get the expressions. From those expressions, one can draw the circuit. Okay? Is that clear? So this is what exactly you need to do it. Let us erase what is not required and try to have some more K-maps. I don't require this. Okay? I don't require this further. Let us take some more tables, K-maps, and try to solve. So what I do is I take a K-map. Now enter the values. What is this exactly? Let's say it is for KC. So for KC values, you see here KC values. Don't care, don't care, don't care, don't care. 1, don't care, don't care, don't care. For which it is 1, for 4 it is 1. For 4 it is 1. And for the rest of the cases it is don't care. Right? So for all the rest of the cases it is don't care. So what I can do, I can combine all of them. What is this? This is QA, this is QB, this is QC. What is this? 0, 0, 0, 1, 1, 1, 1, 0. This is 0 and 1. Okay. The expression for KC is 1. Similarly, if you solve, you will get JB as QA. Okay. Then KB as QA. Okay. Then JA as QC bar. Then KA as well. So this is how you have to do the design. Okay, if it is mod 4 or mod 7 or mod 8, okay, accordingly this table is going to change, and K map you have to use similarly, you have to solve it. With this I will stop.